So last time we talked about some basic properties with graphs. This time we're still going to talk about some basic properties of graphs. We are roughly speaking in section 1.1 of your textbook. I say roughly speaking because a number of the stuff that I'm including in this same first section, your book actually defines throughout the rest of the textbook. He has a tendency to define terms right before we're going to need to use them. And that is a perfectly fine teaching methodology. I went ahead and pulled some of those more at the beginning of class so I didn't throw tons of terms at you throughout. Okay? So a little bit of background, and this is something we didn't talk about last time, and this is what are some of the uses of graphs? Well, it turns out you can use them for all sorts of different things, but they are mainly used as some sort of way to do a picture representation of a situation. It could be as straightforward as something like city streets. That definitely pulls into a graph really, really easy. But that's not the only thing. Anytime you have some sort of objects and there's some sort of relationship between those objects, you can model it with a graph. So for example, some object, let me actually make sure this thing is going to draw for us. Some objects, so object 1. And maybe you have a second object. I'm going to be super lazy and just call it object 2. And then in order to get a graph, you have to have some sort of relationship between them. Okay? If you want to choose between an undirected edge, so it could go both ways, or a directed edge, that's going to be determined by that relation. Okay? So if you have things and say the relation is something like, there's an example that's common in a different course and it deals with people and it says something like is a parent of or is a grandparent of or some sort of familial relationship like that. In that case, it's one directional. Okay? You've got if this person's the grandparent and this person's the grandchild, well, in that case, this is only going to be one direction. Whereas if you have something like, I don't know, plumbing, and this relationship is actually the pipe between your two, I don't know, houses or whatever it is you're doing with your plumbing. If the water is allowed to flow in both directions, let's face it, that's a bad example. Maybe we'd do a different example like a road. Your traffic is able to go in two directions. That would be your undirected edge. Okay? So that being said, there was one thing that we forgot to talk about last time when we were talking about paths, and this is true both of paths, it's true of trails, it's true of walks, it's true of the cycles and the circuits as well. Often people will say, hey, I need a path of length 10. Well, how do you determine the length of any of these guys, the path, the trail, the walk, the circle, the cycle, any of them? And you can replace the word path here with any of those other words as well. It turns out it's simply going to be the number of edges in that path. So, for example, if we have a little teeny tiny baby graph right over here, I don't know, maybe somebody that looks kind of like a bow tie. Okay? In this particular case, if we go ahead and we want a path of length, I don't know, how about length 3? Here's one. It could start at A, it could end at D, and if we actually wrote it out, the sequence that would give you that path, remember, is A, C, E, D, but the actual length of the path is not the number of vertices, it's the number of edges. That length would be 3. I mentioned that because just because of the way the naming is for paths or otherwise, people will often count the vertices, and in terms of length of paths, it's actually the number of edges that you need to worry about. But that was just something I forgot to mention at the end of last time. All right. So here's some new terms. It turns out that we often want to look at graphs and we want to look at how big is this graph. Now graphs consist of two things. They consist of vertices and they also consist of edges. And because they consist of two things, it turns out that there's two different ways to figure out how big a graph is. So in this so what people did is they actually used two different names to determine which they used. Did they count up the number of vertices in the graph, or did they count up the number of edges in the graph? Well, if you count up the number of vertices in the graph, that's considered the order of the graph, often denoted by an O, sometimes lowercase, sometimes uppercase, or just the word order. Okay? And this is simply the number of vertices. So let me actually write that out, number of vertices. So for example, if we have this little bow tie graph again, and let me go ahead and put in the names of our vertices, what would be the order of this graph? Don't overthink it. Yep. So here, if we look at the order of this graph, this guy would totally be just count up the number of vertices or 5. Now, turns out if you want to instead look at how many edges the graph has, you'd look at the size of the graph. And this one here doesn't really have a good symbol associated to it like the other one has with the O up there. So this here is number of edges. So if we wanted to look at the size of our graph G, what would be the size of our graph G? Anybody got a guess? Don't overthink it. Oh, I'm actually hoping that you guys will answer. Yeah, no, if you're just listening to me and not doing anything, it is super duper boring. I am actually hoping for answers from you guys. So yes, totally it's 6. Notice the size and the order are not the same. That's actually pretty common. It's you can have the number of vertices and the number of the edges exactly the same, but most of the time they're different. And depending on what you need, maybe you actually need to know, well, how many edges are in here, and that's going to determine how quote-unquote big your graph is, or you really just are caring about your vertices. Okay? It all depends on what you need to know. So if you ever see the words order or size, it's totally just referring to how big your graph is, one off vertices, one off edges. Now the next things are something that I on purpose skipped last time that ties into adjacent edges and adjacent vertices and incident edges. Now we did the definition. I went ahead and repeated the definition right here. So if you look at adjacent vertices in your graph are vertices that share an edge. Okay. So for example, if we wanted to look at, and I'm going to go ahead and grab the graph that was right up there. If we look at vertex A in our graph in the previous example, do you guys notice or can you guys spot which vertices are adjacent to A in that graph? So I'm going to go with the answer B and C that you guys came in, but I got your question, Tim, just a second. Let me write that down. So yep, the vertices adjacent to B and C, to A are B and C. And the question is, would graph G translate into 5, 6? And the answer is no. So over here in that notation of your graph where it looks like an ordered pair, the V and the E are sets. The order and the size are the cardinality of the sets or the number of objects inside of those sets. So in terms of the actual graph, the V here would actually be listed out for this bow tie graph as A, B, I'm lazy, all the way to E. And then your edges here would be all of those subsets. So A, B is one of them, and so forth. So you won't actually replace the set names with the numbers, although it's very closely related. So the thing that I actually wanted to get to pick up that we had skipped last time relates to these adjacent vertices, and it's something called the adjacency matrix. It's a way to encode your graph. Okay? It is a Boolean matrix, and how it's defined goes as follows. In terms of symbols, there's a couple different symbols you can use. I went ahead and used one of the standard ones, which is just to abbreviate adjacency matrix to ADJ. You then typically have, well, actually all of the ones would then have what looks like function notation and the name of your graph afterwards. I don't know why that G looks like it's smushed. It just happened. And so each of the elements of this matrix are defined as follows. They can be a 1, pointing to the wrong thing, a 0, a 1, or an n. And you remember I just said Boolean matrix. Well, that is true only in some cases. Your Boolean matrix only if you started with a non-multigraph, so somebody who doesn't have multiple edges. So let's define when you get the 0, when you get the 1, etc. So the 0 comes when there's no edge between your two vertices. So this one here, no edge, specifically no edge from vertex I to J. Okay? If your vertices are labeled with letters, put the letters in the appropriate order. Okay? And we'll have an example of that in just a second. Now, a 1 is if you actually have an edge, so totally just a Boolean check. Why did I say no edge? Okay? So this is you do have the edge. And you can also do adjacency matrices for directed graphs as well. In that case, the only thing that would change is instead of having the set of 2 elements, you would have an ordered pair, so you would actually have direction going on here. In a simple graph, you will automatically have non-directed edges, and that means you'll automatically get a symmetric matrix. And if you remember, a symmetric matrix back from linear algebra is the transpose of the matrix is still itself. In other words, if you folded the matrix along the diagonal, it's the same on either side. Now, n. We talked about when n would happen. So this only occurs, so this is the number of edges going from vertex I to j, and this only is bigger than 1 if you're in a multigraph. And that could be a multigraph that has undirected edges or a multigraph that has directed edges. That's actually one of the ways that people spot multigraphs is they have the adjacency matrix out, and then all of a sudden they have something that's not a 0 or a 1. Bam. It's something like a 3. Whoops, there's a multi-edge right there. Okay? So that's the idea behind the adjacency matrix. So what I've got for us is I've prepped up a little example. It actually looks similar to that bow tie example, except it's a little bit less complicated. I guess more like a sideways broom, if you will. Okay? So I've got 3 questions attached to this. And the first one is, what's the order? Second one is, what's the size? And the third one is dealing with the adjacency matrix. Now, since we already had an example on order and size, I'm going to assume that you guys will be able to find that just fine. So what do you guys think? What's the order of this matrix? Okay? What's the size of this matrix? Yeah. So this is one of the cases where the order and size is exactly the same. But even if you accidentally flip them, you're still right. Now, the point of this example was actually the adjacency matrix. So if we want to go ahead and build this adjacency matrix, here's what we'll do. Now, this particular matrix, the vertices are labeled not with integers or numbers. They're actually labeled with letters. So here's how you'd put that together if you have letters. First thing that you do is how the matrix is going to be built is you're going to have all of the rows are going to be labeled by the vertices. You're also going to have all the columns labeled by the vertices. And what I do is when I have letters, I just alphabetize them. You can actually change up or scramble the order, but by default, most people just alphabetize if you have all letters. So first row, I'm going to correspond to A, then B, then C, then D. I'm going to do the same thing when I tag the columns. So I'm going to label each column by one of the vertices. Again, I'm going to alphabetize it. So first column designated by A, second column designated by B, all the way to C and D. Okay. Now, if we look at this first row right here, we are looking at what? Well, we're going to put a 0 if there's no edge between A and any whichever letter we're looking at, whichever vertex we're looking at, and we'll put a 1 if there actually is an edge. This, not a multigraph, so the only numbers we're going to be using here are 1 or 0. So what do you think? Is there an edge in the graph from A to A, or A to itself? Nope, so I'm going to put a 0. And in fact, because these loops technically only occur in a multigraph scenario, if you have a simple graph right here, so simple graph, undirected edges, no loops are allowed, so we'll actually have along the diagonal all zeros. And you could actually fill that in ahead of time if you wanted to. Now when we get to the second one, we have A and then corresponding to B. Do we have an edge between A and B? Yep, so since the answer is yes, we're going to go ahead and put in a 1. Now what's next? Is there an edge between A and C? Ooh, I've got votes for both. What do you guys think? Is there an edge between vertex A and C? Yep, it does turn out there's an edge between A and C. It's right there. And the last thing for the first row says, is there an edge between A and D? Answer is no, so we'll put in a 0. So standard Boolean check, yes is a 1, no is a 0. Okay? So then you can do the exact same thing. Now, since for the next row. Now, we can also totally save ourselves some work. You're in a math class. If you're not super duper lazy, you're probably doing more work than what a mathematician would want to do. Okay? So math is a place where you can be lazy. Now, that being said, you still have to know your definitions and don't do bad math, but we try to do things as lazy as humanly possible. What do we know? We have undirected edges here. So that means there is no direction. So if we looked at the column of A, if we had looked at this first column instead of this first row, would there be any changes in our answers? In other words, would we still get the 0, 1, 1, 0? And the answer here is yes, and this is the thing that I was mentioning before. In an undirected graph, you're going to automatically, the adjacency matrix is its own transpose. And why? That's because the order here doesn't matter, so every row will correspond to its appropriate column. As long as you keep these vertices in the same order. If you scramble the vertices in 2 different orders, that's not going to stay true. Okay? So let's do the second row here. If we look at the second row, we're already done with the first guy. Is there an edge from B to B? Nope, we have no loops here, so that's definitely going to be a 0. So then what about B to C? Do we have any edge from B to C? Yep, so I'll put in a 1. And what about an edge from B to D? Nope, so we'll put in a 0. And because I'm super duper lazy, I'm going to rewrite this same second row as the second column. We've already got 2 of the positions, so I'll go ahead and fill in the 1 and the 0 we just got. So then we can do the third row. Now in the third row, there's only 2 positions left. Anybody have a guess in order what numbers these 2 guys should be? Yep, you got it. So we'll have C to C, there is no loop, so we'll have a 0. C to D, yep, there is an edge from C to D. And I'll go ahead and copy that third row into the third column. There's only 1 entry left. What do you guys think I should put for that last entry? In other words, is there an edge from D to D? And the answer is no, because that would mean there's a loop. That's it for the adjacency matrix. Notice for simple graphs, you'll automatically have the diagonal be 0 because there are no loops, and this upper triangular part is going to match this lower triangular part. Now, that being said, if you have a directed graph where you could have an edge going in one direction but not the other direction, you're not guaranteed the symmetry anymore. You're not guaranteed that the transpose is the same as the original graph. And in a multi-graph, you're allowed to have 1s along the diagonal right here. You're also allowed in a multi-graph to have numbers here that are bigger than 1. So that would be how the adjacency matrix can change with the different types of graphs. Okay? But that's it in terms of adjacency matrix. Questions? Make sense? Feeling okay? It looked like most of you were giving me answers that looked spot on. So the question asked about that there's duplicated information, and if you have undirected edges, yeah, the only thing you need is this upper triangular part. Now, in terms of math, if you're doing it by hand, you'd still take this whole thing because then you'd do stuff with it. In our class, we're not going to do much of anything other than just putting it there. If you actually then, yes, so the order is the number of vertices. The uniqueness of this particular adjacency matrix also depends on how you've written, what order you've written the vertices along the rows and columns as well. In terms of if you want to encode it, people will sometimes, what I'm about to tell you is a pseudo lie. Pseudo because it's true in certain situations. We'll do things like encoding the adjacency matrix as a sparse matrix. sparse is when you have tons of zeros, so that's not true in all cases. But one of the things that you can do if you're encoding it into some sort of computer program, if you're dealing with matrices, one of the programs that's been built for matrices is MATLAB. It actually stands for Matrix Laboratory. But they've got some built-in commands. If you're doing it all by hand, what you would only need to collect this upper half of a matrix, and you'd put it in however you want to encode it, maybe something like a two-dimensional array or something. But yeah, there is some extra information there. In terms of math, though, we just say, hey, it's the adjacency matrix. And if you're writing it out by hand, you still got the whole thing. All right, so there's one other matrix that we'll talk about today. Oh, we actually talked about this already, so we'll go ahead and give you that vertex. There is something called the neighborhood of a vertex, and I am now wishing that I'd put this back when we were talking about adjacent vertices. And this is simply all the vertices that are adjacent to A. So let me go and tag this up here. So in our example up here, the one that looked like a bow tie, where'd it go? This part right here. So the neighborhood of A is all of the vertices that are adjacent to vertex A. So this here is exactly the same thing as the neighborhood of A. We actually already computed it. You can do the same thing right down here with C. You could say, hey, who's the neighborhood of C? In other words, we're the adjacent vertices to C. Well, that would be everybody else, A, B, D, E. So that's just a buzzword, a neighborhood of. We're not going to use neighborhood much, if at all, in this course, although you totally could. But neighborhoods are actually going to come into play with something here in just a second. Okay. So we talked about incidents, or a vertex and an edge that were incident before. Incident means, it essentially means they're touching. Okay. So where two vertices are adjacent because they don't touch, you can get to them, though, across one edge. Incident, you can have two edges that are incident, and they would be two edges that share the same endpoint. Or you can have a vertex and an edge be incident, and that's when the vertex is an endpoint of one. The vertex is an endpoint, one of the endpoints of the edge. Okay? And we talked about that definition last time. But the thing that I want to actually talk about now is the incidence matrix. Okay, so the incidence matrix, and I'm going to do two things for us. The first thing is I'm going to go ahead and label it over here, but with the incidence matrix, it's actually just easier to work it through an example. Incidence matrix. Okay. So first thing is I'm going to go ahead and label the edges so I don't have to keep saying AC for the edge. So maybe we do something like A to B is edge 1, A to C is edge 2, B to C is edge 3, and C to D is edge 4. That just makes me be able to be lazy here in just a second. So here's how the incidence matrix is defined. It is typically denoted by a capital letter I, go figure, I for incidence. Okay? You then label the rows by the vertices. So our vertices here are A, B, C, and D. And let me go ahead and tag that. These are the vertices. And you label the columns as the edges. So our edges were E1, E2, E3, E4. And notice where the adjacency matrix is always going to be a square matrix because you're labeling both rows and columns by all of your vertices. And it's not like you change the number of vertices in your matrix. So they're always going to be square matrix. And that's why we talk about, you could look at upper triangular version of the matrix, or if you prefer lower triangular version of the matrix. Down here, if you have a different number of vertices and edges, this matrix wouldn't be square, and that's okay. All right, so with the vertices along the rows, edges along the columns. Okay? So for this one here, what we're going to do is we're going to put either a 1 or a 0. We're going to put a 1 if the vertex and the edge are incident. In other words, the vertex is one of the endpoints of the edge. We're going to put a 0 if that's not true. So if we look here at vertex A, who is vertex A incidence to? Which edges? Or one edge? So it'd definitely be incident to E1. Would it be incident to any other edge? It'd be incident to both E1 and E2. Notice there's two edges coming in here and touching A. And so all the other edges do not have vertex A as an endpoint. Now, if we look down at vertex B, how many edges are touching vertex B? Right, so there's two of them, both E1 and E3. So we have E1 again, and then we have E3. Don't forget with a matrix to fill in the zeros. I'm not expecting you guys to forget that, but one of my other classes where we do matrices, I swear, like half the time people forget to fill in the zeros. Fill in the zeros. All right, so for vertex C, now for vertex C, how many edges touch vertex C? What do you guys think? Yeah, there's a lot more of them. In fact, everybody except for E1. So it'd be edge 2, edge 3, and edge 4, or E2, E3, and E4. Yes, exactly 3 edges touch. Now, last row, don't forget the 0 like I almost did, just after my little rant about it. So with vertex D, how many edges, or which edge? Yes, you guys totally got it. So vertex D only is incident to one edge, specifically E4, and let's close off that guy. Now, do you notice anything interesting about the incidence matrix? Hint, you could look across the rows, but I would recommend looking down the columns. Right, so there's no guarantee that you're going to have a transpose here. And in fact, if you do, that would be far more rare than if you didn't. So this one, don't assume symmetric matrix. In fact, it's actually rare that we even have a square matrix at this point. But if you look down the rows, specifically looking at the ones, how many ones are in each of those columns? I said rows, columns. Look at the columns. You want to look at the things labeled by the edges. Yeah, there's 2. Now, it turns out as long as you're doing the incidence matrix of a simple graph, so a regular old graph, it's undirected edges, no loops, no multi-edges, what happens, it turns out for each edge, what happens? Each edge always has 2 endpoints. Okay, let's face it, that's actually true all the time. Yeah, you just said it. So what goes on is, like, for example, that first column, you looked at E1, we put a 1 for both B and A, so the first 2 rows of, yes, and that's why you want to, so the question was, what about loops? If you're in a multi-graph, you could have loops, and in that case, that's the only case where your edge would only have a single endpoint. So yeah, you guys are spot on right there with that question. But as long as you have an edge that has 2 different endpoints, which is the only thing allowed in a simple graph or a standard digraph or a standard directed graph, you wouldn't have that case of the single loops. But that'll occur in your multi-graph scenario. But I just wanted to point that out. Like, for example, here, if you go down if we had filled these in according to rows instead, not rows, we did rows, columns instead of rows, as soon as we got the first 2 ones, we would know that the rest of these guys would have to be zeros. And it turns out there's a relationship between incidence matrices and adjacency matrices, and we're totally not going to go over that today. All right, so that takes care of the basics of some of the ways that you can actually encode these guys. There's another thing that you can do if you are creating the incidence matrix of a directed graph. Notice here, there's not a good way of indicating where the directed edge started or stopped. It turns out people use positive and negative ones for a directed edge of where it starts and where it stops. And in that case, you would have at most 1 positive 1, 1 negative 1, and then the rest of them would be zeros in a directed graph. Again, that's excluding loops. All right. So this actually gets us into talking about the degree of a vertex, and you can do degrees of vertices in any of the types of graphs: simple graphs, directed graphs, multi-graphs. So I'm going to focus in on simple graphs right here. So suppose we're in a simple graph, and suppose we are looking at some vertex. The degree of that vertex is simply count up the number of edges that are incident to the vertex. In other words, how many edges touch your vertex. Now, another way of thinking about that, it's also exactly the same thing as this neighborhood. Why? Because if it's the same thing as the number of vertices adjacent to A, well, the only way you're adjacent is if there's an edge between vertex A and whoever the other guy is. So the other way that you can think of this is You can totally think of it as the cardinality of the neighborhood of A. I had one other way prepped up. Did I have any secondary awesome way? Oh, it was tagging back to the adjacency matrix. Okay. So let's look at an example first. So if we wanted to look at this guy, and we'll do at least the degree of some of these vertices. So say we look at the vertex here, and the degree of said vertex here. And some people prefer a column like this, 2 columns, and some people prefer 2 rows. It doesn't matter. So if we look at these different vertices, and I'm definitely regretting having this many vertices in the graph. Oh, well, it'll be fine. What do you guys think? What would be the degree of vertex A? Any guesses? You got it. 1. Anybody have a guess for the degree of vertex B? Yep, 2, because there's 2 edges here touching vertex B. Any guesses about the degree of vertex C? Don't overthink it. Yeah, it's the same as vertex B. What about for the degree of vertex D? Back to 1. Yep. What about the degree of vertex E? Again, back to 1. And the only one that's actually a little bit interesting in this graph that almost looks like a starfish except for that one little like triangle piece. Any guesses the degree of vertex F? Yep. That's it. Actually, if we didn't have this edge here, BC, this guy would be called a star graph because it kind of looks like a starfish. We'll have names of graphs later, not today. Okay. But that would be it. That would be all that you're dealing with if you're looking at degrees. Okay. Now, in terms of this guy, you can also look at degrees inside of the adjacency matrix, and it's literally looking across your rows or columns and counting up, hey, how many guys am I adjacent to? So I'm going to go ahead and say that this one here is also exactly the same as number of vertices, vertices adjacent to A. And technically speaking, that's exactly the same as the symbol in the middle there. Okay. So that would be degree. I think, actually, let me see if I can put it in the middle here since we've been talking about it, degree of a directed graph, just because that is a little bit, it's similar but a little bit different. So in a directed graph, you can't just talk about degree because there's a direction. So what you've got is something called an in degree and something called an out degree. Anybody have a guess on what those 2 guys are? Don't overthink it. It's again going to be the number of edges doing something. Yep, it's totally going to be the number of edges going into your vertex or the number of edges going out of your vertex. So your in degree is going to be the number of edges coming into the vertex as coming into vertex A. In terms of a picture form, bam. And it's also an out degree, number of edges going out or going away from whoever your vertex is. We'll call it vertex A again because I was too lazy to change the name. So like that. That's it. So if we have some little baby example here, relatively small, since this is totally freehand, it's not going to look quite as nice as the other one where I tried to get the computer to snap the edges straight. So we'll have C, we'll have B, we'll have D. I was attempting to get a square figure. I should have just drawn a square and then put in the edges. Oh, well. Double. Yeah, that did not look like a square figure. Apparently my career in art is not going to happen. All right. So suppose you have something like this. I didn't do anything fancy in terms of, oh, I missed the question. Sorry, I was reading it. Yes, so even though directional edges or edges with direction, look like little arrows or they look like little vectors. They're not actually called vectors. They will still have two endpoints. They have, some people call them a head and a tail to designate where you start. So where you start, like if you're a CD edge, you'd start here at C and you go to D. Okay. So in this particular case, let me actually put a chart for us here as well. We've got 4, so I can put a chart in. So here we've got our vertex. Can't just do a single degree. I mean, you could sum them together, but it typically doesn't give you the information that you want for a directed graph. And if you have a directed multigraph, the same thing works here. Your degrees are bigger. Okay. So if we look at vertices A, B, C, and D, awesome, that's going to fit. If we look at vertex A first, so right here, what do you guys think the in degree would be of vertex A? Yeah, there's 2 of them going in. Bam. What do you think the out degree of vertex A would be? And that's literally all you have to do. So the only difference in a directed graph is instead of just looking at all the edges that touch your vertex, you'd now have to look to see, all right, what direction are those edges going? Are they pointing in or are they pointing away from the vertex? And that's literally it. So if we looked at vertex B here, so over here, what do you think the in and the out degree would be? They would both be what? Yeah, they would both be 1. I like those of you who put it in pairs. That was really smart. Better than the way I ask it. What about for vertex C, right down here at the bottom? What do you think the in degree would be, and then second, the out degree? In degree? Yep. 1 for the in degree. There's only the edge A to C coming in, and then the other 2 edges are going out. And last guy is vertex D. What do you guys think about the in and the out degree for those guys? Yeah, both 1. Notice anything about your in degrees and your out degrees. There is actually a property in terms of their relationship. Anybody spot it? It's not super straightforward, so, ooh, good call. So if you add up all the in degrees and you add up all of the out degrees, they are going to be the same. Why? Because there's exactly 1 arrow head and exactly 1 arrow tail per edge, and that sum, yes, will totally be the number of edges. It turns out that there's a property that we'll get to probably in chapter 2, I think it's where your author talks about it, that says if you sum up the degrees in a regular simple graph, you actually get double the number of edges. Why? Because you counted each edge twice for each of the 2 endpoints. Here with the directed graph, though, you're not doing that. If you only sum up your in degree, that's going to be the same as the number of your directed edges. Sum up the out degree, also be the sum of your directed edges. It's a way to check to see if you're right in terms of did I get the right degrees here as well. Especially if you have a directed multigraph and a loop involved, then you got to worry about some extra things. Actually, you guys want to see what you would do with a directed loop here? Okay. So let me put in 1 directed loop. It is going to change our answer, so let me put it, how about at B? So let me move B. So B is over here. And we'll go ahead and erase the answers for B. Oh, I should not have done B. I really should not have done B. Undo, undo. Wow, that's the slowest undo ever. We'll put it at C. Just tuck it in there. All right, so if we go ahead and put a loop down there at C, the in degree and out degree of C, vertex C is going to change. Nothing else is going to change. Any guesses what the new in degree would be, if any change? Remember, in degree is the number of arrowheads coming in. Yeah, I like one of your guys' comments. And let me point that out after I read it. So the new in degree would be 2. And the comment that I was trying to point out was actually somebody else did too. Yes, both of the degrees, the in degree and the out degree, would go up by 1. And that is because for this loop, we have both an in and an out part of that arrow, or part of that directed edge. So here we'll get 2, and we should have, what, 3? For the out degree? Yeah, it looks like 3. So that's the key thing with the loop, and this is something that is easy to forget, is people will often forget to include the loop whatsoever in the in and the out degree. But what happens if you don't include the loop? When you count all of the in degrees up or you add up all the out degrees, you won't actually get the right number, and that would be the number of directed edges in the graph. So that would be something to watch out for. And this now with the loop is a directed multigraph, just because of the loop. All right. All right, so that's the basics of degrees. That's the basics of incidence and adjacency. So the next thing is actually a different topic. Any questions before I move on? All right, so the next thing I've got for us is the definition of a subgraph, and then we're going to look at connected graphs. And we've actually already talked about connected graphs a little bit, but I wanted to make sure to show you some examples and then give the official definition of bridges and cut sets. Even though we talked about them last time, we couldn't define them because we didn't have some of the terminology yet. Okay? So in terms of a subgraph, a subgraph is literally just like a subset. A subset is part of a larger set. A subgraph is part of a larger graph. So if you have some larger graph, so G is some vertex set combined with some edge set. So let me go ahead and put a little graph over here. I actually really like that bow tie graph, not going to lie. It actually is the quintessential example for something we're going to do in Chapter 3, one of our properties. Not properties, one of our types of cycles that we're going to look at in Chapter 3. Not Chapter 3, Chapter 2. I'm all over the place, sorry about that. But it's a really fun graph to draw too. So suppose you have some graph like this guy, and let me go ahead and put some labels on the vertices. I was not in any way, shape, or form creative about those labels for the vertices whatsoever. But if you have a vertex set and an edge set, so here a vertex set are the 5 vertices, then we have the 6 edges. We've looked at this graph before. If you want a subgraph of this graph, here's what has to happen. Your subgraph would also have a vertex set and an edge set, but its vertex set, W, has to be a subset of the original vertex set. In other words, the only vertices you're allowed to use are vertices that were in the original graph. Some people grab all of the vertices and they don't like to change it at all. That's totally fine. Some people only grab some of the vertices, and that's also okay. Now, the second condition is on the edge set. You also pull edges from the original set of edges in the original graph. So this guy here would be our original graph G. Now, here's the deal. If you don't use all of the vertices from the original graph, you're not allowed to use an edge that uses one of those vertices you didn't pull down to your subgraph. Okay? So there's an extra stipulation on this edge set in the subgraph, that guy. So the endpoints, really both endpoints, of every single edge inside your new edge set must be in that new vertex set W. Okay? So you don't get to have an edge that only has one endpoint, not allowed, in other words. So here, let's grab a subgraph. There's tons and tons of possibilities. What vertices would you guys like to use? It doesn't matter, you just have to pick some selection from A through E. Anybody have some vertices they want to use? Yeah, sure. We could do A, C, and D, and actually a number of you said that. So I always like to put them in the exact same orientation as from the original graph. Now notice what this means. If we're only going to pull A, C, and D, we're not going to use vertices B or E. That means we automatically are not allowed to use any of the edges BE, BC, or CE. In other words, any of the edges that have B or E as an endpoint. Okay? So that means we are looking, when we're looking at our subgraph, we can now only pull any of the edges in this part of the original graph. Now, we don't have to use all the edges. We could totally pick some of the edges. Maybe we pick A and D. Maybe we pick D and C because my little stylus was already down there at D. Maybe we decide not to use the edge AC. That would be one option of a subgraph. And we'll look at subgraphs in the future. Actually, one of the things that we'll look at in the future is trying to find subgraphs that look in a very particular way. And we're going to say, hey, does this graph actually have this type of this type of other graph as a subgraph. It'll be something that we'll look for. Okay? But that's the definition of a graph, of a subgraph, excuse me. It's just graph inside of another graph. You're only allowed to use your vertices and edges that you started with, essentially. They essentially sort of glossed over that condition. Okay? Questions about subgraphs? Kind of okay so far. All right, so sort of related to subgraphs. So no, that is actually a really good point and something we're going to see here in just a second. We're about to jump into connected and disconnected graphs. Yes, a single vertex can totally be a subgraph. So another option of a subgraph is, here actually let me give you a couple more options. So another option is subgraph would just be the vertex B. And another option or another possibility of a subgraph of that original graph G is something like AD and BE. And if you wanted to be really annoying to your readers, maybe you actually included all the original vertices, but only those last two edges. Yeah, no, it does not need to have any sort of edge. Your only edges you're allowed to use are from the original graph, but your subgraph does not have to be connected. It can be in multiple components. You don't have to include any edges if you don't want to. You can include 0 edges up to all of the original edges, although to be fair, if you started with a connected graph and you included all of your edges, you would get the original graph back. So this one here, the new edge set would actually be the original edge set, if I'm reading what you're asking correctly, yes. And so we're going to apply what you guys just asked dealing with connected graphs. Okay? So it's going to look kind of similar to some of these subgraphs that were looked at, although that's the only connected subgraph. All right. So we talked about the definition of a connected graph last time, and a connected graph, formally speaking, goes as follows. It still has a vertex set and an edge set, but it says take any 2 vertices where those vertices are not the same vertex. Okay, so make sure they're properly different vertices. So any pair of 2 different vertices, then there has to exist a path, and you could actually call it a trail or a walk too. This part doesn't matter, but by default, most people deal with paths. Okay? There exists a path from A to B. Okay? In other words, you can literally start from any vertex in the graph. You can end at any other vertex in the graph, and you can get there. It may only be one way to get there, but you can always travel along the edges of the graph to get to that second vertex. Now, that being said, let us look at some examples. Okay? And I believe I have 5 examples here prepped up. You can only see 2 of them right now. So the question here is going to be, we're going to start with just identifying if these are graphs that are connected or disconnected. So disconnected is just not connected. And then the second question we're going to ask is we're going to look at the definition of bridges and cut sets and go back to these same examples. So that's what we're planning on doing, and that'll probably get us to the end of time today. So what do you guys think? First 2 graphs, are either of them connected or disconnected? Yeah. So it turns out here that the first one is totally a connected graph. Not going to lie, most people totally think of connected graphs as just what a graph should be, myself included often. And disconnected graphs really look like 2 different graphs that are sort of just sitting next to each other. Okay? One of the things that people will do in terms of showing that you have a disconnected graph is they'll often put some sort of dashed line. If I'd actually written those example graphs in something that was other than red, I'll typically do a dashed red line, or like what I did right there, a highlighter color. Why? Notice I was able to put a slash or a line through the graph and separate the vertices and the edges of the graph into 2 different places where there's no edges that cross that highlighted line. That right there, in terms of a visual picture, is a way to show that it's disconnected. Now, that being said, we've identified that the first 2 graphs, one's connected and one's disconnected. What about I think we can actually get the last 3 graphs. The last three graphs are G3, G4, and G5. What do you guys think here? Do we have any that are connected or disconnected? Oh, you type fast. Yep, so the first one here is connected. Second one, also connected. And the last one is about as disconnected as you can possibly be. Now, why would I say that? Because there are no edges whatsoever. So we have multiple options here. We've got several different cases of connected, and we had the previous connected one as well, and then one disconnected. And that's it. That's if you were ever asked to identify as a graph connected or disconnected, that's literally all you'd have to check. Questions so far about connected and disconnected? Ooh, yeah, good question. So here, graph G5 is disconnected because while we have all vertices, specifically you have more than one vertex. So suppose we had a G6, which I'm going to fit in really, really small right down here. So G6, if you just have a single dot for G6, and let me actually put a line here so we can see the difference between those ones that have pieces, that guy would actually be connected. And that would actually be the only time that you would have vertices and no edges and still be a connected graph. Why? Because you only have that one piece, that one vertex. So yeah, good call on the edge case there. Other questions about connected, disconnected? We're about to do something more with them, but I want to make sure the basic questions are all answered before we jump to the slightly more than basic thing. All right. So the next two things that we want to look at are a bridge and then a cut set. So let me start off with a bridge. A bridge is specifically an edge in your graph. Okay? And you are also in a connected graph. So don't overthink this. Bridges, technically, you could look for edges that act similar to bridges in disconnected graphs, but technically bridges are only defined if you started with a connected graph. So when we go back to our examples, we're going to look at our connected graphs that also have edges. It's not going to be in that last example because there's no edges. Okay? So it's an edge, you're in a connected graph, and this is the condition to be a bridge. If you remove that edge, then the graph turns into a disconnected graph. In other words, there was only one edge that prevented your graph from being a disconnected graph. Okay? So keep that in your head. We're looking for one edge that if we remove it, we change a connected graph into a disconnected graph. I'm going to go back to these examples. Okay. Start with the top one. So the top one up here, we said it was a connected graph. This is G1 that we're looking at. And the question that we have is there a bridge in this connected graph? What do you guys think? Is there an edge that we could remove and get it to be disconnected? And you're totally right. Actually, all of the edges are bridges. Yeah, as many of you said. So for example, maybe we picked on this guy. That one totally would be a bridge, but let's actually write it over here to the side. All edges are bridges. And this actually ties back to the size of a graph. Remember, size was the number of edges you have. When the size of the graph, so the number of edges, is relatively low as compared to the number of vertices, you're far more likely to have more edges to be bridges. Now, that being said, it all depends where the edges actually live in your graph. So that's not a sort of catch-all. It's more of a sort of, I don't know, broad strokes type thing that often is true, but not always. All right, so that was the first connected graph. Now let's go down here to G3 and G4. These were the only other two, the only other two connected graphs that had edges. So if we look at these guys, and let me go ahead and put in some vertices. So A, B, some labels on the vertices, C, D, and E, super lazy, just going around the outside. And down here, A, B, C, D, E, and F on that one as well. So what do you guys think? For G3, does it look like there's any bridges? Yeah, In terms of this one right here for G3, it turns out there's actually no bridges. If you tried to remove this center one, you would just get a big cycle. If you tried to remove one of these over here, it would just kind of look like a pincher shape. You could still reach somebody, maybe not the same path you would have normally, but you still can get to all of the other vertices. So this is one of the situations where you have no bridges whatsoever. So that's the other extreme case as opposed to G1 that had all the edges were bridges. Now, when we go down here to G4, what do you guys think? Does it look like there might be any bridges there? Yeah, so it turns out there's several bridges, and it all depends on where you want to go. You've got a bridge, where is it? There's a bridge right here, A to F. If you removed AF, you'd have the single vertex A and then everything else. You also have BF. If you removed the edge BF, you'd have a single line and then the cross-hatching stuff. And the other one, I believe you guys said this one too, was BD. If you remove that one, you'd have the single vertex D and then everything else. So let me actually write out those bridges. The bridges were AF, BF, and BD. Okay. Ooh, so if you do have a vertex, so the question is talking about a point is incident to only one edge. Typically, it's actually rephrased in math. We normally say if a vertex has degree 1, so like for example here A and D, if the vertex has degree 1 or it's incident to exactly one edge, then yes, automatically it's going to be a bridge because why? As soon as you remove this edge, there's no other edge connecting to that vertex, and that vertex will then be all by itself. So yeah, good call there. Now, not all bridges are formed that way, but if you have a vertex in that scenario, then you're going to have the edge attached to that bridge, or incident to that vertex will be a bridge. All right, now notice this guy here, it had bridges. This guy was connected but no bridges, and this leads us into the cut set. Okay? So the cut set is where you don't have bridges. So this, well, I lie. A bridge is actually a cut set, a type of cut set. So a cut set is some set of edges. It's actually okay to have only one edge, but that's when you'd have a bridge. Again, you're in a connected graph where if you remove the entire set of edges right here, then the graph will be disconnected. Okay? So to respond to the question in the chat, some people respond to me, contact me not publicly to everybody. So as long as it doesn't look like a confidential question, those are the ones I try to repeat ahead of time. So this one here, cut set, is dealing with a set of edges, connected graph. If you remove the whole complete set of edges, then your graph is disconnected. Now, if you have bridges, automatically each one of these guys are a specific type of cut set. So I'm only going to look at, can we find a cut set in G3, the guy that had no bridges but was still a connected graph. So what do you guys think? Do you think we could actually find a cut set in graph G3? In other words, can you find 2 or more edges that you could remove to make that graph disconnected? Hint, you can always find a cut set. Worst case scenario, you remove all the edges. Don't remove all the edges, although that's perfectly fine. Typically, what we like to look for is the minimal cut set. It's rarely unique. So a minimal cut set is simply one of the smallest cut sets you can grab. Did anybody spot a cut set? Yeah. So make sure I grab the same one you just said at C. Yep, that was the one I was thinking too. How these guys are typically denoted on the graph itself is typically with a line like that. In a class scenario, yeah, the one at A will also work as well, so you can do it over here as well. And those would be the 2 minimal cut sets. If you're doing it on your own paper, people like to do it in pencil, whatever. It's just some sort of slash through the graph. So a minimal cut set here would consist of 2 edges. And I'll do the one you guys sent me first, which is BC and CD. Although the other one at A would also work. You can also Oh, yep, you're right. There's a third one at D as well. And you can also do a cut set here at E, but E would not be a minimal cut set because it would have 3 edges. And you can also do one, let me get the color, right there. That's not just cutting off a single vertex. This would be actually having 2 graphs on either side, neither one just a single vertex. And that cut set would consist of the 3 edges that intersect that line. So the cut set is always the edges that intersect that slash that you put through the graph. This would also be a 3-edge cut set. You can. So the question is, can you just pick a vertex with the smallest degree and grab its edges for the minimal cut set? Often that works, but that won't always give you the minimal cut set. There are cases where, and it didn't happen in this example, but there are cases where the degrees of the vertices are higher than just, say, 2 edges that connect different components of the actual graph. But it's a good first check, though. And in the future, we'll actually go through finding minimal cut sets. There's actually a whole algorithm that we'll work on in Chapter 3 that's all about finding the minimal cut set and making sure that that really and truly is that smallest possible cut set. But I totally accidentally didn't check the time, and we are definitely done with time, so we'll stop there. Next time, we will finish up section 1.1. We've got a couple of extra examples of I don't really want to say story problems, but they're sort of application problems. And then based on time, we'll start section 1.2 either at the end of next time or the day after. Okay? But that is it for today, unless you guys have extra questions.